So far, we've seen how there must be an assignment that satisfies at least 7/8 of the clauses in any 3CNF formula. And in fact, the same argument gives us an algorithm that satisfies 7/8 on average. Just pick a random assignment. By itself, however, this does not guarantee that we'll actually find an assignment that satisfies 7/8 of the clauses. To obtain such a guarantee, we're going to use a technique called de-randomization that will take the randomness of our algorithm out and give us a deterministic algorithm with a guaranteed 7/8 factor approximation.
An important part of the algorithm will be a subroutine that assigns a value to a variable and simplifies the clauses. We call this procedure instantiate. Let's say that we want to set a variable x1 to true. Then any clauses not involving x1 are simply left alone. And if a clause has an x1 in it, then it gets set to true. If a clause has a not x1 in it, then we just eliminate that literal from the clause. If not x1 is the only literal in a clause, then we just set the clause to false. Another important subroutine will be one that calculates the expected number of clauses that will be satisfied if the remaining variables are assigned true or false uniformly at random. Of course, if a clause is just true, then it gets assigned a value 1, and a clause that's just false gets assigned a value 0. A single literal gets assigned a value 1/2, two literals gets assigned a value of 3/4, and three literals gets a value of 7/8. Remember that there's just one way to assign the relevant variables so that the clause is false. The E of y procedure simply calculates these values for every clause and then sums them up using the linearity of expectation. With these subroutines defined, we can now write down our de-randomized algorithm as follows. We start with an empty assignment to the variables. Then, for each variable in turn, we consider the formula resulting from the variable xi being set to true and the one resulting from xi being set to false. Between these two, we pick the one that gives a larger value for E of y. That is the one where the expected number of satisfied clauses is greater, assuming that the remaining variables are set at random. Note that we're using our knowledge of how a random assignment would behave here, but we actually aren't using any randomization. Having picked the better way of assigning the variable xi, we update the set of clauses and record our assignment of the variable xi. The reason this algorithm works is that it maintains the invariant that the expected number of clauses of C that would be satisfied if the remaining variables were assigned uniformly at random is at least 7m/8. This is true at the beginning, just by our previous theorem. But this expectation is just the average of the expected number that would be satisfied in CP and the expected number that would be satisfied in Cn. So by picking C to be the one for which this E of y is greater, the invariant is maintained. Of course, at the end of the algorithm, all the variables have been assigned, so this expectation is just counting up the number of true clauses. This technique is known as the method of conditional expectation, and it has a number of clever applications. Overall, then, we've shown that there's a deterministic algorithm which, given any 3CNF formula, finds an assignment that satisfies at least 7/8 of the clauses. Remarkably, it turns out that this is the best we can do, assuming that P is not equal to NP. For this argument, we turn to the concept of probabilistically checkable proofs.